Okay, the tonometry, one of the most interesting um, technical method to measure pressure. The basic principle is when a pressurized vessel is partly collapsed by an external object, the circumferential stresses in the vessel wall are removed and the internal and external pressure are equal. This approach has been used quite successfully to measure intraocular pressure and has been used with limited success to determine intraluminar. We have some mistake here. Intraluminar arterial pressure. The force balance technique can be used to measure intraocular pressure based on the Imbert-Fick law. With this technique, the investigator measures the force required to flatten a specific optically determined area. Forbes et al. In 1974 developed an applanation tonometry without touching the eye. An air pulse of linearly increasing force deforms and flattens the central area of the cornea. The instrument consists of three major components. The first is a pneumatic system that delivers an air pulse, the force of which increases linearly with time. I call it air gun. The second and the third component, the system that continuously monitor the applanation and the status of curvature of the cornea, determines the occurrence of applanation with microsecond resolution. Two obliquely oriented tubes are used to detect applanation. One transmitter tube T detects a collimated beam of light at the corneal vertex, and two, a telecentric receiver R observes the same area. In the case of the undistributed cornea, the detector receives little or no light. As the cornea's convexity is reduced to flatten condition, the amount of light detects is increased. When the cornea is applanated, it acts like a plano mirror, this is L, plano mirror with a resulting maximal detected signal. The current source for the pneumatic solenoid is immediately shut off when applanation is detected in order to minimize further air pulse force impinging on the cornea. A direct linear relationship has been found between the intraocular pressure and the time interval to applanation. Okay, let's review all three previous pages on this schematic diagram. As you can see, we have two systems to transmit light and receive it. Undistributed cornea here and the air gun some optical devices to focus the received light on the detector, and let us to explain again. We send a collimated light to the distributed corner, the center of the corner. Because of the convexity of the cornea, the light beams will be scattered and cannot focus on the detector. but applying the air pulse on the center of the cornea, and after application of the center of the cornea, this region will act as a plano mirror and will reflect good the transmitted light. Therefore, we can focus, we can collect more light on the detector, and we can find the maximum location of the received light, and also therefore we can, because of the controlling pressure applied by the controlled pressure applied by this air gun, we can find the exact pressure applied by the gun on the cornea. Therefore, the maximum value of the receiving light is the index for finding the pressure applied on the cornea. And based on that principle, when we have a membrane, when we have a border, a flattened border, it means that the pressure at both sides of this border is equal, intraocular and extraocular. The pressure at the outside applied by this air gun and the pressure inside the ocular. When these pressures are equal, the membrane, the border is flattened, and this is the key for solving this problem. Therefore, as I told you before, tonometry is one of the most technically tuned method to measure pressure inside our eye. Also, we can use that interesting method for measuring pressure for arterial tonometry pressure measuring. The principles of operation of arterial tonometry are very similar to those for the ocular tonometry discussed before. Continuous measurement of arterial pressure throughout the total heart cycle can be available in this method. The instrument sensor is placed over a superficial artery that is supported from below by bone. As you can see here, we have an artery here, a bone at the bone below this is the bone below the vessel, and based on that principle, that common principle, we will apply a pressure and we will try to find the flatten situation for the wall of the vessel, and therefore we can find the pressure inside the vessel. And also we can continuously measure the pressure inside the vessel non-invasively. Arterial tonometry suffers from relatively high cost when compared to a conventional sphygmomanometer, but one significant advance of the arterial tonometry is its ability to make non-invasive, non-painful, continuous measurements for long periods of time. As you can see, we push the wall of the vessel. We assume that we have a frictionless piston here, and based on some equations, we can find the pressure simply by applying a specific force on this situation. And we will try to flatten the area under the sensor. Echo indicates that several conditions must be met by the tonometer sensor, and an appropriate superficial artery for proper system operation should be considered. Bone provides support for the artery opposite to the applied force. The hold-down force flattens the artery wall at the measurement site without occluding the artery. It's important. We don't want to stop the flow of the blood. Compared to artery diameter, the skin thickness over the artery is insignificant. The artery wall has the properties of an ideal membrane. The arterial rider is the part of the system we will use to apply the force, and also we will use to measure the pressure. The arterial rider, positioned over the flattened area of the artery, is smaller than the artery. And also the force transducer spring constant Kt is larger than the effective spring constant of the artery. One of the most important issue we should consider in this part is that the multiple element sensor necessity in recording pressure by arterial tonometry. A major practical problem with the above approach using a single arterial tonometry is that the arterial rider must be precisely located over the superficial artery. A solution to this problem is the use of an arterial tonometry with multiple element sensor. It can be one of your questions in your exam. Also, the hold down force F1 for each subject must be determined before tonometric reading can be taken. The hold down force is gradually increase or decrease while recording the tonometry sensor output. As you can see in this slide, a multiple sensor element is used to find the best location. We have a robotic system here, and it will search to the best location, the best position. We have multiple sensor, and as you can see, the central sensor will measure the highest value, and the lateral one will record less values of pressure. And the best position, in the best position, we have symmetrical responses from the sensors, as you can see. If this is assume that this is the vessel, if we locate the sensor here, the output of the sensor will be something like this. This is not good. But if we locate the sensor exactly at the center of this vessel, we have an output. We have an output like this. This is a symmetrical output, and this is good choice for recording because the sensor is located at the center of the sensor. The multiple element linear array of force sensors and arterial riders are used to position the system such that some elements of the array is centered over the artery. And about the arterial tonometry fabrication, we can mention these cases. Multiple element tonometer sensors have been manufactured from a monolithic silicon substrate using anisotropic etching to define pressure sensing the diaphragm. And also piezoresistive strain gauges in the diaphragms are fabricated using integrated signal IC processing techniques. The strain gauge resistance is used to determine the pressure exerted on each sensor element. In this slide, you can see some examples of piezoelectric pressure sensors we can use in the rider of the system to measure the pressure inside the vessel.